First, let me introduce our jury group. I am Fu Zuyi, come from National Taiwan Normal University. Here is Professor Chen Hongyi, come from National Taiwan Normal University. Professor Lu Pinghua, come from National Taiwan Normal University. Professor He Peiming, come from National Taiwan University. Professor Yu Jingzhong, come from National Kaohsiung University. Now, let's introduce your group from the poster.
Good morning, everyone. My name is Alex Chaudhry. I'm captain of All Magazine, and I have, No Magazine, and I have Thomas, Richard, Darren, and Cedric. Thank you.
Opponent.
Hello, everyone. We're Team Meet from National Experimental High School, and I'm Captain Xie Chenhan, 段一鸣、刘尚伦、戴云杰 and 赖一晨. Thank you.
Dear judges and fellow competitors, I'm Chen Xinwei from Team Lao Xian. This is Zhong Yaoxian, Xu Yiyou, Hong Shaokai, and Su Yuan. Thank you.
你们的时间呢？好 ，challenge please.
We would like to challenge question number 2, relate this.
We reject number 2, related.
We would like to challenge problem number 12, strange motion.
You can't challenge that. I thought you pulled it as well.
他说他们已经报告过这个题目，应该不能再报告。
他应该是，就是他是说 oppose 的时候 ，oppose 过的是 opponent 这边 oppose 过，所以 reporter oppose 过的是没有观点的，就是他的 A B C D 那4个。
手册上面有写，所以你们 oppose 过的，我们还是可以打。
哦，对啊，因为在这上面的记录有。那
we accept number 12 strange motion.
The accept is 12. Please write down your name on blackboard. Now full name, please.
This is number 12, stage motion. I am from No Matters and my name is Alex Jr. The following statement says, sprinkle small floating particles on the surface of water in a bowl. Bring a strong magnet above and near to the water surface. Explain any observed motion of the particles. Our main focuses of the problem will be 1. What particle materials allows the particle to move? 2. How does the magnet create particle motion? And 3. What parameters affect the observed motion of the particle? We'll begin with the preliminary experiments where we would show our demonstration and note down some observations. We'll then continue with an explanation of non-uniform magnetic fields and particle alignment. Then we'll move on to a theoretical model where we'll map the magnetic field, potential energy, and magnetic force graphs. Then we'll continue with experimentation and discussion with setup, drag, and acceleration comparison. Then we'll conclude. We'll start with a demonstration. So this demonstration is a test of ferromagnetic powder. So here in the reflection you can see the bar magnet from over top. You also have some you have iron particles which are ferromagnetic because it's Fe2+ over here, and you can see that they roughly align. So our observations: ferromagnetic particles attract and move across the surface of the water. Paramagnetic and diamagnetic materials do not move very much. They move minimally but not very much. And also particles orient towards the magnetic field almost immediately, and that particles tend to align and stick together when in motion, and that effect is called clumping or buckling. And 5 is particle speed depends on the proximity to magnet, because obviously the closer you are to the magnet, the stronger the magnetic field. So here are the 3 materials we use. We have 3 types of magnetic substances, so we have 3 types each. So for ferromagnetic substance we use iron powder, for paramagnetic we use copper oxide, and for diamagnetic we use zinc oxide. So here's our phenomenon demonstration. Want to click again? No, double click. No, bro. Sorry, this time. Double click. Yeah, so here's our paramagnetic copper oxide. You can see the small dots over here, they're not moving very much. And the diamagnetic zinc oxide too, they're not moving very much, which supports that theory. So we tested paramagnetic and diamagnetic materials shown over here, and we used strong neodymium magnets, which are basically the strongest magnets there, and by holding them over the top of the water surface. So 7, a basic explanation overview of this topic is that a permanent magnet will generate a non-uniform magnetic field. And ferromagnetic material domains, internal domains, they are able to realign to this magnetic field. And the variation in the magnetic field B surrounding the permanent magnet will orient the particle and attract it, as that video should play. Go back. Or maybe the video already played, I don't know. So, go back. As I mentioned earlier, it generates a non-uniform magnetic field. The internal domains are randomly assorted in ferromagnetic materials. Over here, they're randomly aligned. And when exposed to a certain magnetic field, they will realign. And the external beta B field will form an alignment of the domains. So we also map the magnetic B field over here using the Python matplotlib. We map 3D magnetic fields in the X, Y, and Z directions for B, and obviously, as we mentioned earlier, the closer they are, the larger the B. So that is our map. We use a vernier magnetic field probe. Notice how we had a plastic. We specifically used a plastic surface because we know that the permeability of plastic is close to that of thin air. So the permeability of that won't be a confounding variable that will affect it. We also had an elevation and range for XY change, so we can keep things constant. So here is our general theoretical model. So B vector represents our magnetic B field. But what we did is we assumed that we projected the entire force onto the xy plane, because we're focusing on the motion on the water, not focusing on the motion in the air. So this will be our total magnetic field, and we're matching it onto cosine theta xy, where theta is this angle. So you're going to have cosine theta xy is going to be that, and B is equal to that. And we use this model for further potential energy calculations. So when we assume simultaneous alignments, this is a general shape of the particle. It's shaped like an ellipsoid. We define our coordinates and variables like this. We can use torque calculations to find how they spin and align. So here's our torque calculation. Torque is equal to I alpha, which after some simplification, you can get some partial differential equations that can, you can have some second order differential equations that can be solved. And for some certain variables, like for example, we did a sample calculation over here of these variables. The time it takes to align will be roughly 0.007 seconds, which justifies our assumption of simultaneous alignment since that number is very small. And an important thing to note that as the alignment angle near 0 in cosine xy coordinate, this automatic alignment kind of oscillates a little bit for stopping. So next, our potential energy. This is very simple. You all probably know this. This is a potential energy calculation mapped onto the xy plane, and this is also our theoretical graph of what it would look like. So these are our equations graphed onto positional matrices. So to graph the magnetic force, you know force is equal to the negative derivative of potential energy. So we use Python local gradient function using adjacent points to estimate the magnetic force across plotted xy coordinates. Note how you can't just directly take the derivative. You have to take the gradient derivative. So gradient of f is equal to partial x, partial y, partial f over partial x plus dot dot dot. And then you will get this equation after plugging it into a computer. So this is a visual representation of a graph that shows the gradient of the function. So here is for we define m as the magnetic dipole. So this is for inaccurate force predictions, and this is for accurate force predictions where the magnetic dipole is equal to, it's proportional to the external magnetic field. Note that we use a great polynomial prediction curve to find f of x, y based on coordinate x and y positions. And here we have that. So next we move on to experimentation and discussion. So first we sprinkled iron powdered particles into glass tanks filled with water. Note how iron particles are ferromagnetic, so we can observe their motion better. Then we dropped a bar magnet into a secure position over here. We have neodymium magnets, as I mentioned earlier. And that magnet will track the particle attractional motion. And we have our phone on top of that thing, which will track the motion of the particles. Here is a diagram of the tracking software we use. It's called Tracker, which can help us find the position versus time of certain particles that we're tracking. And obviously, after that, you can take derivatives and do the analysis we wish. So here's our experimental results and discussion. So we used a second order gradient from the original position versus time graph shown over here. This is a sample graph, and we determined acceleration versus time, which is very trivial. Next, we want to account for the water-resistant drag force. Since we mentioned earlier that the particles are shaped like ellipsoids, we can use Stokes' law set over here and a correctional force over here. And that will give the drag force we want. So we also plotted acceleration versus force for constants, so then we can at least to support our argument. So acceleration versus force graphs to determine the slope of c over m. So when you're plotting acceleration versus force, you obviously know they're supposed to be proportional. So here's our relative graph. You can see that there's a good slope of c over m correlation with x and y graphs, and that values generally overlap with some error analysis. You can see that the error is relatively low. So here's a comparison of the acceleration. And one thing I want to note about the deviations is that the n deviations actually illustrate another interesting phenomenon called bulk of particle alignment. This will cause some limited accuracy in accounting for force decreasing as you approach the magnet's axis due to that same bulk alignment. We compared experiment acceleration and predicted acceleration, obviously using error bars and error analysis. You can see over here, they align pretty well. and the predicted accuracy using a coefficient of slope and slope C over n. We determine the error bars and the slopes. So let's talk about this interesting phenomenon called accounting for bulk particles. So an interesting thing to note is that oftentimes a lot of certain ferromagnetic particles will come together. And when they come together, they have some internal domains that will align. So actually, the total force will, the total magnetic field will be the external magnetic field, which is obviously caused by the magnet, plus the alignment and bulking of these internal bulk particles, which will cause a field by themselves. So to account for them, the particles bulk and align together. There's a pretty nice demonstration video, which will cause the unaccounted increase of B. Because if you remember from our graph, there's some stuff over here. That's due to the accounting for bulk particles. And you also notice that the number of aligned particles will vary over time at the situation. And we use this formula to account for extra particle magnetic field remnants. And another thing I want to mention is the difficulty in predicting near the magnet axis. Because when you're trying to observe and model the phenomenon, as we mentioned in our experimental setup, we have our camera hanging over and our magnet. But it's difficult to see what's happening directly below the magnet because the camera is above the magnet. And if you move the camera, you're going to have reflections and divergences in the water, and you're also going to have changes in angle that you have to account for. Note here that the force should slightly decrease when in very close proximity because there the potential energy is lower and the potential energy peaks at the local maximum for stable equilibrium. So in conclusion, so ferromagnetic particles have visible motion. The force of attraction relies on the change in magnetic field. The acceleration of individual particles adequately is explained by a model as indicated by the good fit that we showed earlier. And we also note that the particle bulking increase the magnetic field change because they form some simultaneous alignments that create their own magnetic field themselves, which will generate more magnetic field. And here are some future work. So we want to investigate our generalizations for accounting for particle bulking, and we want to measure our precise magnetic fields that are near the magnet to account for small forces decreased during the magnetic axis that is difficult to measure. Thank you.
So starting with, can you turn to page 4, quickly? So I believe that you said that you see a motion here, but however, I believe that should be a picture. Can you please show me like what the motion is? Because we're talking about motion right here, but that's a picture.
Excuse me. I think there's another slide where you can see the particles realigning, but I think no, stay here. But my point in this slide is that if you have a kind of particle shape like an ellipsoid, and you have a magnetic field here, it's going to kind of realign so that the length is
okay, so basically it comes closer and then forms a sort of line.
it aligns its length to the magnetic field.
Oh, okay, no problem. So the next question is, so you believe that the motion is caused by the characteristics of just these particles, so the liquid has nothing to do with this?
If you go back to the problem statement at the very beginning, near the water surface, note how it says water, not other liquids.
Well, yeah, I know it's just talking about water, but do you think that any characteristics of water might also affect the changes to your experiment?
What do you mean by experiment? Do you mean final velocity? Because obviously, if you increase the viscosity.
I mean, just do you think that any characteristics of the water would also affect the phenomenon to happen? Will also allow each phenomenon to happen? Just yes or no?
There may be. I'm not quite sure what you're referring to.
Okay, then can you turn to page 19? I just want to make an clarification of what the force is right here. I'm not really
Here is the video you're probably watching.
okay.
So this is the graph of the force in the x direction.
Yeah,
This is
what
the
force? What force?
magnetic force.
Oh, okay, so the magnetic force of the whole system. And then the next one, did you keep all of the magnetic field same in the whole experiment?
It's kept at a constant place. As you see from our experimental setup I mentioned earlier, the neodymium magnet called by a certain.
Time's up.
Thank you.
水分走不进去。那像水分走进去，就是它接着往下。
And today I'll be opposing on question number 12, spring motion. So as we can see right now, so for the problem statement, we can see right here that it says that we should sprinkle a particles on the surface of water, and then we should observe the movement, and then also explain the phenomenon and then also investigate on it. So our crucial point is to explain the motion that is observed. So we can see right here that first we have the small floating particles and also the surface of water. So the first question that would bring us is why, if the small particles affect, and the second question that would bring us is why we should use water. So next, summary in the reporter's report. So for the phenomenon, they basically said that ferromagnetic particles would move, and then paramagnetic and diamagnetic particles would not move, or that they're not significant enough for us to observe. And then the ferromagnetic particles would align according to the magnetic field of the magnet. So for the theory, they mapped the magnetic field to the XY plane, since we're only talking about the movement on the surface of water. And then they also used Stokes' law, and then also gave potential energy. And then for the experiment, they made predictions and also used tracker to track the points. And then after that, they take other phenomena into account, such as the bulking of particles. Okay, moving it into the pros and cons of the report. So he gave clear explanations of the use of equations, and then also they had experimental data supporting the theory that they were supposed to use, and then also they had predictions towards the result, and it actually fits the experimental data. So the cons is it did not clarify what errors he considered during accurating his data, and then the next would be he lacked of explanation of why he chose the equation to support his model. And then the next would be lack explanation of the effect of the water, which is why we should use water in the problem statement. So moving on to what we're supposed to discuss later. So first we're going to talk about diamagnetism, paramagnetism, and then also ferromagnetism, like different kinds of magnetism, and then describes how these characteristics might affect the phenomenon that we're supposed to use. And then we're also going to define the motion, or to clarify what motion we're expecting to see, and then what they actually saw. And then for the theory, we're also going to talk about such as boundary conditions for a phenomenon to happen, for example, in under what conditions, or also under what intensity of magnetic field should these all be discussed. And then also the parameters. So they gave some parameters, but we believe that there are some parameters that we could discuss and then maybe put them into the report in order to make the report better. So first is the size of the particle. Since they describe the characteristics of the particles, however, they only describe characteristics such as basically how the particles react to the magnetic field. However, we believe that there could be more parameters to investigate on the particles in this experiment. And then also, we also want to talk about the intensity of diamagnetism or paramagnetism of the particles that they use, because we believe that maybe by changing that we can have different results on the experiment. And then also we would like to add some parameters such as the intensity of magnetic field, which we believe could be changed and could bring on more data to the experiment. Thank you. So first, let's move into the discussion. So first, I wanted to can you please explain to me what do you think the difference of motion in these of the three particles that you used are different? How they're different and why they're different?
As I mentioned, I'm assuming you're referring to ferromagnetic, paramagnetic, and diamagnetic particles. And as I mentioned earlier, those three materials have different inherent properties, and that the ferromagnetic materials have internal domains that are randomly assigned, and when exposed to an external magnetic field, they are able to realign, whereas the other two cannot. So in the context of this phenomenon, since they don't realign, the motion of these particles is really minimal, and it's difficult to measure unless they have themselves a certain magnetic or metal property that makes them attractive to the magnet.
So you're saying that the diamagnetism particles and the paramagnetism should not?
That's not what I said. Excuse me for not being clear. As I mentioned earlier, they don't have internal domains that make them align simultaneously. So they may have minimal motion. They may have minimal motion that align them along their lengths, but as shown by modern literature and our experimentations, they have a negligible effect in comparison to ferromagnetic materials.
Okay. So from what I believe, I think diamagnetism is supposed to repel the external force, external magnetic force acted upon these particles.
Such as water. Water has. But I will note here that for what I know, the repelling properties is 10 to the negative 7, which is 10 million.
Yeah, it's really small. But however, we also have the Paul-Lagrange theory, which could describe the scale of the diamagnetism in each particle. And do you believe that by using that and then changing the particles, we could reach to maybe we can maybe find the particles which a diamagnetism particle which would actually have the motion in your experiment?
Excuse me, by changing what?
The intensity of the intensity of diamagnetism of the particle.
The intensity of diamagnetism of the. I don't understand what intensity of diamagnetism refers to. If you are a diamagnetic material, you are diamagnetic. It's not a. Can you explain what?
So I believe for the Paul-Lagrange theory, it's supposed to describe the intensity of magnetism, and it looks like this, where it's related to the r theta, this one right here, which is the mean distance from the electrons to the electrons, and then there's also the mass, and then also the number of electrons and then also the number of atoms in a unit volume.
Excuse me, what I heard was the distance between electrons and the number of electrons and I'm not quite sure what you're referring to, and you're also saying the total number of electrons. So from what you're implying, let's say you have a diamagnetic particle of mass 0.03 kg, and you have a diamagnetic material of mass let's say you have 3 kg. So you're saying by changing the mass of the particle, you're going to increase the diamagnetism.
I believe that the mass should be referring to the atom instead of like the whole thing.
The mass of, so instead of like hydrogen or carbon, actually they're not metals. So heavier metals?
So yeah, sort of things like that. So they might change like these parameters might change the how intense their diamagnetism they have. So I believe that maybe by changing the particles, and then we can maybe reach a motion that can be observed.
Excuse me, I must respectfully ask again what you mean by intensity. What are your units for intensity? I don't understand.
For my part, I kind of forgot.
Excuse me, if you're trying to find intensity, then and you don't know what intensity is, then I really don't know what you're referring to.
So basically, well, it's from my intensity, I mean like how strong how strong the characteristic of this particular particle is. So
what characteristic? Its mass, its magnetic field, its attraction, its volume is what?
It's related to all these, but it's maybe.
Well, of course it is. You wrote it down.
Yeah.
So what does this mean? So what does intensity mean? You have many types of intensity.
That means the availability for it to become a magnetic. I think it's a magnetic moment, and so when we have this one, which is smaller than 0, we call it diamagnetism. But when it's bigger, so we kind of call it paramagnetism, right?
Yeah. So actually, I was thinking about this earlier. I was going to point out to you that it's actually on the scale of the magneticism is on the scale of diamagnetism to paramagnetism and to ferromagnetism. So, but I was really confused when you say increasing diamagnetism, but because that would imply moving closer to magnetism, or even moving into paramagnetism. So, by increasing diamagnetism, you're changing it to paramagnetism and then changing to ferro. And I don't think, even if you are right, which I respectfully disagree, as I mentioned earlier, it only has a 10 to the negative 7 effect, which is 1 in 10 million. Whereas even the bulk particle phenomena at least account for 12% of the phenomena.
Okay, so what I'm trying to point out is that maybe you can try to use different diamagnetism particles, but if you don't agree with me, that's okay. I want to talk about more on the effects of water. Do you think that the water would cause, so from, you just said, you also believe that water has diamagnetism, right? So do you think that that characteristics would also affect the experiment, like affect the particles?
Excuse me, I apologize, but I'm not quite sure if I said diamagnetic or paramagnetic, but I do know that water has a property that would make it repel the magnet. But could you please repeat your question again?
So it's diamagnetism, right?
Yeah. So could you please repeat your question?
Do you think that the diamagnetism of water would also affect the motion of your particles?
The magneticism of water would influence the motion of particles?
Yeah.
Well, yeah, if they create some kind of a field within themselves, then they would align towards an extra field. But again, as I said, 1 in 10 million isn't really, you really shouldn't account for that when you could be including other important phenomena like bulk particles. That would explain that deviation perfectly.
Well, from what I believe that when the water is trying to repel the magnetism of the magnets, so they might actually cause a little curve right here. So I think it's on page maybe 14 or something where you maybe actually 8 where you explain your phenomenon. Can you move back one more? Just a few more. you have this graph where you have like a particle and then also the curve of the water. Can you show that to me?
Curve of the water.
Yeah, so just
Yeah,
the
we did.
particle with the, oh yeah, this one. So can you
But this was talking about drag.
yeah, I know, but so you're saying, can you turn back to the, yeah.
Drag.
So can you turn,
Excuse me, I mean, this one.
so this one, can you tell me what affects the, what causes the curve right here?
Neither, we're talking about drag over here. So this is
Yeah.
this is Stokes' law. If you're talking about water repelling, first of all, there's no magnet. Second of all, if you look, you don't need to look closely. This is
Oh,
flat.
yeah, okay, so that's,
This is a particle accounting for drag. This has nothing to do with
okay,
magnetism.
so that may be my, that's my fault, but what I'm trying to say that the diamagnetism of water may cause like a curve right here, which causes a, like a, in the, not hump, well, like a hole in the water in order to make the particles like move in another way. Do you think that might be true, or do you still believe that it's just too small to connect that?
Type 101 is, I think, 800 meters tall, so that would be analogous to it moving down 1 millimeter in the context of Type 101, which I think is, yeah.
Okay.
So, no, I don't think it's relevant when we have so much other things to talk about.
Okay, so then would you, do you think that you might be able to change the to change the intensity of magnetic field in the future in order to like, explain the boundaries?
Yeah, we did. We have a graph for that. Changing the F. Quick.
Time is up.
Oh, here.
Oh,
Nah, it's alright.
oh, okay, thank you. Oh, okay, so I'm going to summarize this discussion. So we're basically talking about the possibility of changing the particles, which might have different characteristics on the motion. However, the reporter didn't agree with me, which he believes that even by changing the magnitude of diamagnetism, they are still too small to neglect. So and then we also talked about like how water would the diamagnetism of water would affect the motion. However, the reporter still believed that the magnitude was too small in order so that we can neglect it. Though I hardly believe that, as I think there are experiments where we can see the diamagnetism of water. So that's why I don't think that I kind of disagree with the reporter. Thank you.
Okay, now I'm the reviewer, and for the reporter, I have a question. Do you think that to observe the motion, we have to use water as a liquid, or we can use other sources?
We can use other sources, but as I mentioned, earlier, the problem statement mentioned water only.
Okay, thank you. And for the opponent, you mentioned that because of the diamagnetic properties of the water, they could cause a damping in the surface. So, do you think that different solutes in the water would affect this effect?
Yeah, I do believe so.
So you think that okay? Now I understand. And for the opponent, and you mentioned that the magnetic field of your magnet has three ways, but you said that do you think that the z-axis will affect the phenomenon? Because you only mentioned the x and y axis.
Would you please turn to the x where I mapped out its way? Yeah. So what we did was we mapped it so we have a vector B field in this direction. So because the magnet is held above this layer, there will be we're not observing the vertical motion of the particles. There's obviously gravity, surface tension, etc. pulling it down. So we mapped it onto the xy field.
Okay, thank you. And how do you know that the particles are aligned?
Excuse me?
How do you know that the particles are aligned?
Oh, I think we had even a calculation for, I think, yeah, it's this one. So we define it to be aligned when we model our...
So the align is based to your definition of alignment. Is that correct?
Yeah, it's based on...
Okay, thank you. And the next one, how could you have such small time intervals? Because since you put in your presentation with a 0.007 seconds of interval, what equipment did you use in your?
This was a theoretical calculation.
So you didn't observe that. It's just a theoretical.
This is a
model.
theoretical.
Okay, thank you. And that's about all. Thank you. Good evening, good morning, fellow competitors and judges. I am Max Su from Team La Passion. Because of some equipment problem, I'll just say my report. Now, the proper statement says that spring small floating particles on the surface of water. Yeah, but that is not that is empty. So that's just a template. So I have to speak, and you have to listen. Sorry about that. I bring a strong magnet about and near to the water surface, explain any observed motion of particles, and their focus is what particle materials allows the movement. Now, the reporter has some. The phenomenon is like the problem described. The theory is that the ferromagnetism is to the particles and magnetic force that allows the movement. And the experiment used strong Mendelian magnets and mainly used iron powder for the experiment. And the strings are clear demonstration of phenomenon and clear model made for the movement of particles. But their weaknesses are they didn't mention the Moses effect. They misunderstood the problem statement. Particles, not only paramagnetic particles. And the next one is their tracking technique is not complete. For the opponents, the summary of their presentation had mentioned the summary of the reporter. Their strengths are they pointed out several places the report missed, but they didn't mention the most of the missed points. Now for discussion part, the opponent first asked what is the difference of the motion between the different particles. The reporter replied that they have different internal properties. But the reviewers agrees that the particles should all move, whether ferromagnetic or not, but with different reasons, along with the trivial effect. And magnetic phenomena can be magnified significantly. And the next question is that the definition of intensity, and the reporter and the opponent discussed that throughout these, so the reviewer have no comment on that. The next discussion is the diamagnetism of water's motion on water's effect on motion. And the reporter replied that they create field within themselves, like the diamagnetism of water's effect on motion, since they created a field within themselves. And the reviewer agrees with the opponent that the diamagnetism of character of water causes the formation of the water surface, then allowing the particles on the surface to move. Now, for the points missed part, both teams has neglected the Moses effect, which is the diamagnetic water deformation that causes the surface to drop below average. And next one is the trivial effect, which is an effect that allows the two particles to come closer because of the liquid's properties. And next one is only some data points have error bar in their reporter's explanation. And the report mentioned that they use a strong magnet, but they mentioned consistently that the magnetic field is not strong enough, which is strange since they said that it is a strong magnet. And the next one is that we believe that a field of around 0.5 T is enough to cause a deformation of 0.1 mm, and which can be observed, but the reporter replied that they couldn't observe. And the final one is that we suggest for a clear phenomenon observation, you could use a stronger light source to observe the movement of the particles on the surface. And that's about it. Thank you, bro.
Here are my concluding remarks regarding this discussion. First, I would like to clarify that I do agree that the water, as I mentioned multiple times before, will repel the magnet extremely gently and cause bare movement. But I really don't think we should be spending 4, 5, 6 minutes on the topic that we call this 10 to the negative 7 movement when we have so much other things we did talk about in our presentation that merited some discussion. I was a little bit confused on one of the reviewers' points about magnet being too strong but not being able to observe it. We did observe the ferromagnetic material alignment, but I disagree on the paramagnetic and diamagnetic material alignment. Even modern literature suggests that such motion is fairly negligible, and I think such an attempt to refute that would be pretty futile. I also disagree with the opponent on one of the reviewer's questions, which he asked her. She replied that the material inside the water will change the properties of the water, which I disagree because they are separate substances. I also did not understand the purpose of the diamagnetism intensity question because it seems very clear to me that magneticism is based on the gradient, and the changing of the strength would redefine the opponent's whole point of the question and thereby invalidate the claim. So those are my concluding remarks. Thank you.
The estimation of our thing seems to be not working. So because theirs is working well anymore, so maybe you could modify it.
Okay, we will do it then.
他说他的是好是坏，这个连接性好是有问题。他说在
他其他笔电可以，所以说是我们对啊，是我们自己问题，没事。
那你们其他笔电上面？
对，所以你们在比赛前要测。
应该是每一个电脑都要测测看，看哪一个电脑是可以最顺利连接的。对，因为其实有时候因为 challenge 的题目不一样嘛，我也知道大家准备的不一样。对，所以如果有任何一个电脑不能连接，就是要早一点到会场来，就稍微。
我们理解规则。
好。所以今天这就是那个推荐你，推荐投资你，推荐。Please.
I have a question for the reporter. You mentioned some 10 to the minus 7 effect with diamagnetism. What did you mean by that number?
I think what I meant by that number is that I saw, I read that the effect of the magnetic field due to the magnetic properties of repulsion is as a ratio to the magnetic field due to the magnet itself is only 10 to the negative 7.
Say that again?
Excuse me. So the reporter mentioned that, the opponent mentioned that there would be a little deflection in the water. So my point was that the deflection only accounted for 10 to the negative 7 of the total magnetic field movement.
The deflection is a depth, right? Measured in depth. The magnetic field is measured in a different unit.
Right. But sorry, my point is the strength caused to deflect this is, I'm not talking about by how much it deflects. I'm talking about the strength required to deflect that in comparison to the strength used to move the other particles in the xy direction.
But if I say there's another material which would be more easily reflected than water, would you say that the intensity of the diamagnetism of that material is stronger?
Excuse me, could you repeat the first part of your question?
So you were saying that the diamagnetism has a strength of 10 to the minus 7 something.
Sorry, no, that wasn't. I'm saying the 10 to the negative 7 is the ratio between the strength of the magnetic field that
but you were using that number as a qualification of how diamagnetism is important or not.
Oh, excuse me, I was using that number to attempt to disqualify the argument that the depression of water is an impervious phenomenon to investigate in this field.
I have a question for Gio. For the reporter, you mentioned only ferromagnetic material can move in this question, right?
I think I mentioned earlier that there will be movement for diamagnetic and paramagnetic. So as we discussed earlier, even for diamagnetic materials, the deflection of the water will only be 10 to the negative 7. So there will be.
You mean it's just no motion to observe?
Excuse me?
Three types of material you observe.
Yeah.
Only the first one you can see.
Only ferromagnetic
Yeah.
and you observe.
Is it? Do you agree?
I hardly agree with that because I believe that because of the diamagnetism of water, they actually can cause a movement in diamagnetism particles and also paramagnetism particles.
So you can observe with different kind of material.
Yes.
We believe that we agree with the opponent that if the magnetic is strong enough, because of the diamagnetic properties of water, any particles on the surface may move if the magnet is strong enough. Then we can observe that.
Excuse me, but I included a video with our neodymium magnet, and that video clearly showed no observable
Okay.
motion.
Okay. Yes. Answer is yes.
Any other questions? Okay, please repeat the grading time.
再提醒一下，因为他们刚才是不得已，他想要换成这个电脑，然后把档案通过去。对，但是资料的话，我们会再提醒。
对，要这样对，就是全部都会这样。要这个全部都会这样。
对，再重新讲一次，对。就说并不是报道的那一台电脑不能开网络，是所有的网络都可以开。对。
The marking point for reporter 7, 7, 6, 5, 7. For opponent 7, 8, 8, 8, 6. For the viewer 7, 8 7 7 8。然后我们必须要在这边再强调一次哦，就是一下子我们的那个休息时间的话呢，各队呢你换过位置以后呢，一定每一台电脑全部都要测，可不可以接那个连接哦？对，因为有的时候呢，好像从昨天就有发生，就是有些。